Okay, continuing this section 1.3. Now we're going to define trees as a graph and also forests. All right, so a tree is a connected graph that contains no subgraph isomorphic to a cycle. So a connected graph that has no cycle. Okay. So here is an example of a tree. And you can see that there are no cycles, right, in that graph. So, all right, so that's a tree. And then a forest is a graph that contains no cycle. So, a forest is not necessarily connected. You can see this graph definitely contains no cycle. The graph is these two together. And so you can see that there is no cycle in here, but it is not a tree, right? Because it's not a connected graph. All right, some easy to prove items about forests and trees. So every connected subgraph of a forest is a tree, right? So because a forest would contain no cycle, if you had a connected subgraph, right, it would be a connected graph that contains no cycle, right? If the big graph contains no cycle, well, then the subgraph can't contain a cycle either. So every connected subgraph of a forest would be a tree. Every subgraph of a forest is a forest, right? So same reasoning there. If I have a subgraph, a forest contains no cycle, right? And so, if I have a subgraph, it can't contain a cycle either. And so therefore it has to be a forest. All right, every subgraph of a tree is a forest. So again, if a tree if I have a tree, right, it's a connected graph with no cycle, and so therefore any subgraph is not going to contain a cycle either. So that automatically makes it a forest. And then this one is odd, right? Every tree is a forest. Because a tree, right, is a connected graph that contains no cycle, and a forest is just a graph that contains no cycle. So that one's pretty much automatic. All right, so there are some of the relationships there. All right, so that brings us to theorem 1.3.2, right? If G is a tree with P vertices and Q edges, then P is equal to Q plus 1. And we've pretty much already proved this one because of the fact that its proof goes very similar to the theorem that we proved before about this theorem about the connected graph with P vertices and Q edges, that P is less than or equal to Q plus 1. So for a tree, right, it's that it's equal to Q plus 1. All right, so let me get this set up. All right, and the proof is again same thing by induction, right, on the number of edges. All right, our base case is once again P0. P0 looks like this. Right, and that is the only tree with one vertex, right? And we can see, right, it's connected, it has no cycle. And if we look, right, check P equals Q plus 1, well, it has one vertex and 0 edges, so I get 1 equals 1. So it checks out, right? It satisfies the theorem. All right, so next up is our induction hypothesis. And our induction hypothesis is that if G is a tree with P vertices and less than or equal to n edges, fewer n or fewer edges, right? Then P is equal to n plus 1. All right, so we get to assume that is true. And what we want to show is that if G is a tree with P vertices and n plus 1 edges, then P is equal to n plus 1 plus 1, so P is equal to n plus 2. Okay. Oops. Said 2, but I wrote 1. All right, and so how would that go? All right, so suppose I have this G, right? It has P vertices it's a tree, right? G is a tree. P vertices, n plus 1 edges. Well, find the longest path in G. All right, and in the proof of the theorem I showed you there previously, right, we said that the endpoints of the longest path, right, have degree 1. So we are going to look at, take one of those edges, right? Or take one of those endpoints, rather. Of the longest path and delete it. Let's call that A. And look at G minus A. All right, because because A is an endpoint, we know that G minus A is connected. Right? Because it's an endpoint, it's degree 1, right? So the graph, may come down here and look like this. But if this is degree 1, if I delete this one, this edge here, and this vertex, right, what remains is still going to be connected, right, because of the fact that it's an endpoint at degree 1. All right. Further than that, G is also a tree, right? Because as we mentioned before, sorry, I shouldn't say G is a tree. We already knew that, right? But G minus A is a tree. right? It is a subgraph of a tree, right? And so therefore, it's going to contain no cycle, right? And we already know it's connected, right? So it has to be a tree, all right? So G minus A is a tree with P minus 1 vertices and N minus 1 edges. Okay? And so therefore, the induction hypothesis, right, since this has N or fewer edges, oops, sorry, let's see. It's, N edges, right? Right, G had N plus 1 edges, right? So if I delete 1, I come up with N edges there. All right. So the induction hypothesis implies that the number of vertices, right, of G minus A, which is P minus 1, is equal to the number of edges plus 1, right? And so I get P equals N plus 2, which is what we wanted to show, okay? All right, so by the principle of induction, mathematical induction, we now know that the theorem is true for all non-negative integers. Okay, so that's the proof of this theorem 1.3.2. All right, next up we have the other way. Suppose G is connected and P equals Q plus 1, then G is a tree. Okay. So we're going to prove that one by contradiction. All right, that is, we are going to suppose G is connected and also that P equals Q plus 1, that is the number of vertices of G, right, is P, and the number of edges is Q, right, and P equals Q plus 1, but G is not a tree. All right, so if that's so, right, since G is not a tree, G must contain a cycle. All right, so let E be an edge on that cycle. All right, so if the edge E lies on that cycle, then G minus E is connected. Right? And it has P vertices. Right? We didn't delete any vertices, only deleted an edge, and it would have Q minus 1 edges. Right, G had Q edges. Then we deleted one of the edges, right? So now G minus E would have Q minus 1 edges, okay? All right, so remember we talked about theorem 1.31, right? And that said that in any graph, we have, or any connected graph rather, we have that the number of vertices is less than or equal to the number of edges, which for G minus E would be Q minus 1 plus 1, all right? So this is for, again, for G minus E, right? It has P vertices. It has Q minus 1, right, edges. So by theorem 1.1, we know that P has to be less than or equal to Q minus 1 plus 1. That says that P is less than or equal to Q. All right, and if P is less than or equal to Q, then it certainly can't be equal to Q plus 1, so this is a contradiction. Therefore, our assumption that G is not a tree, right, must be false. So therefore, right, G is a tree. All right, and I think that's it for that one. All right, and we will split this off into its own video.